In this video, we'll delve a little deeper into the regression model, but to do so, we'll need to revisit a core idea that was inherent in ANOVA and analysis of variance, and that's partitioning the sum of squares in our outcome variable. Except now, instead of partitioning the sum of squares based on group means and deviations from those group means, we'll partition based on predicted scores and deviations from those predicted scores. In other words, we'll partition the sum of squares into information that we can understand and predict from our regression model, and information that we don't understand even after doing our regression analysis. To start, we first have to recognize how each person's outcome score can be divided into three pieces. To illustrate this, let's return once more to our previous example in which we used ratings of Empire Strikes Back to predict ratings for Jar Jar Binks. Let's consider a person who gave a rating of 1 for Empire and a rating of 5 for Jar Jar Binks. We can look at the value of their outcome variable, their Jar Jar Binks rating, as being equal to the overall mean Jar Jar Binks rating plus the difference between their predicted score and the mean, plus the difference between their observed score and their predicted score. Now remember, in our previous video, we determined that the predicted score for someone with an Empire rating of 1 was 4.084. So for this specific person, this works out to their outcome score of 5 being equal to the mean, which was 3, plus the difference between their predicted score of 4.084 and the mean of 3, which is 1.084, plus the difference between their observed score of 5 and their predicted score of 4.084. 5 minus 4.084 is 0.916. Once we see that we can take the outcome scores and break them into pieces related to differences between our predictions and the mean and observed scores and our predictions, let's calculate the sum of squares for the outcome, breaking or partitioning that sum of squares into those same pieces. Now, again, this is very similar to what we did with ANOVA, except now we're looking at deviations from the mean and predicted scores instead of deviations from the grand mean and group means. Okay, so here's our equation. Let's subtract y bar, the mean of y, from each side. We now have a positive and negative y bar on the right side of the equation. These cancel out, leaving us with y minus y bar equals y hat minus y bar plus y minus y hat. We'll now square both sides of the equation and then sum across all individuals. Next, we'll expand the right side of the equation by first writing out both of the squared terms and then multiplying out the corresponding terms. Now, we'll need a little more room. And let's expand the right side of the equation. The sum of y hat minus y bar times y hat minus y bar is just the sum of y hat minus y bar squared. Similarly, the sum of the observed y minus y hat times the observed y minus y hat is just the sum of the observed y minus y hat squared. Then we have the sum of y hat minus y bar times the observed y minus y hat. But our last term in our expansion is just the same thing written in reverse order. So we have 2 times y hat minus y bar times the observed y minus y hat. So we end up with the sum of yi minus y bar equals the sum of y hat minus y bar squared plus the sum of yi minus y hat squared plus 2 times the sum of y hat minus y bar times yi minus y hat. Now, similar to what we see in ANOVA, the product of those deviations of predictions around the mean and deviations of observed scores around the predicted scores end up being equal to 0, and so it will drop out of the equation, leaving us with the sum of yi minus y bar squared, or the sum of squares total, equals y hat, the predicted y, minus the mean y squared and summed across all the participants, which we call the sum of squares regression, plus yi minus the predicted y squared and then summed across all the participants, which we call the sum of squares residual. Phew! Now, while in regression we talk about the sum of squares regression, it's functionally the same as the between group sum of squares in ANOVA. We're just looking at the sum of squares related to the regression line rather than groups. Similarly, the sum of squares residual in regression is functionally just like the within group sum of squares in ANOVA. It's the sum of squares related to someone's score that we don't understand based on our statistical model. In fact, you may see the within group sum of squares in ANOVA referred to as the sum of squares residual or sum of squares error sometimes. And that's okay. It's functionally the same thing. Given that we've partitioned the sum of squares total into the sum of squares regression and the sum of squares residual, it would be informative to determine the proportion of that total sum of squares that's related to the regression and the proportion that's related to the residuals. That's very straightforward. You simply divide both sides of the equation by the total sum of squares. That leaves you with 1 equals the sum of squares regression divided by the sum of squares total plus the sum of squares residual divided by the sum of squares total. Now, the sum of squares regression divided by the sum of squares total tells us the proportion of the total sum of squares that's related to the regression equation. And the sum of squares residual divided by the sum of squares totals tells us the proportion of the total sum of squares that's unrelated to the regression equation, that unknown error that we can't predict yet and still need to explain. Let's take a closer look at the sums of squares regression divided by the sums of squares total. And let's divide both the numerator, the sum of squares regression, and the denominator, the sum of squares total, by n minus 1. Now, we can do that because the two n minus 1s are going to cancel out in the end, so it doesn't actually change anything. But wait a second. Sum of squares divided by n minus 1, that's the formula for a variance. So that's the same thing as saying that it's equal to the variance related to our regression line divided by the total variance in the outcome. Now, the sum of squares regression divided by the sum of squares total is the proportion of the sum of squares that's related to the regression equation. But it's also the proportion of the total variance in the outcome that's related to our regression equation. It's the same thing. Another way of saying this is that it's the proportion of the variance in our outcome that's related to or accounted for by the relationship that the outcome variable has with the predictor. But that was also the description that we had for R squared, the correlation coefficient squared. The beauty of all this is that it means the sum of squares regression divided by the sum of squares total is also equal to the proportion of the variance in the outcome accounted for by our regression equation. It's the same thing, mathematically and conceptually, as the R squared. So we'll talk about the sums of squares regression divided by the total sum of squares as the variance that's accounted for by our regression model. Similarly, the sums of squares residual divided by the sums of squares total is equal to the proportion of the variance in the outcome that is not accounted for by our model. It's the proportion of the variance that we still don't understand, that error around our regression line. This is equal to 1 minus R squared. And these two proportions will always add up to 1 or 100% of the variance in our outcome. Now, the sum of squares regression divided by the total sum of squares tells us the proportion of the variance in the outcome that's related to our regression model. But of course, any model will almost certainly be related to some variance in the outcome just by chance. Even if there's no effect, no association, we don't expect the sum of squares regression to be exactly equal to 0. So we're back to that question of what's big enough to reject the null hypothesis? How large does the sum of squares regression over the sum of squares total need to be in order to conclude it's so large in our sample that it must be greater than 0 in the population? We previously saw with ANOVA that we could use the F-test as a way of doing that when we had a categorical predictor. When we were looking at whether there were differences between 2 or typically 3 or more groups on some outcome. Given that we calculated the F-test in ANOVA by partitioning the variance, and we just saw that regression involves partitioning the variance in a very similar way, it's probably not a shock to learn that we can use an F-test as a way of testing whether the variance that's accounted for by our regression model is statistically significant. That's actually just another way of saying that we're testing whether the R squared, or just the correlation coefficient itself, is statistically significant. Now remember, the F-test in ANOVA was the sum of squares between groups divided by the degrees of freedom between groups. All of that divided by the sum of squares within groups divided by the degrees of freedom within groups. In regression, it's functionally basically exactly the same thing, just with slightly different labels. We're talking about regression instead of between groups, and we're talking about residual instead of within groups. It's just the names have changed. It's kind of like that old TV show Dragnet.
Ladies and gentlemen, the story you are about to see is true. The names have been changed to protect the innocent.
In ANOVA, the numerator of the F-test was the sums of squares between divided by the degrees of freedom between. In regression and multiple regression, the numerator is the sums of squares regression divided by the degrees of freedom regression. And in ANOVA, the denominator of the F-test was the sums of squares within divided by the degrees of freedom within. In regression and multiple regression, it's the sums of squares residual divided by the degrees of freedom residual. This F tests the overall regression model, whether the model accounts for a statistically significant amount of the variance in the outcome. In simple regression, that's R squared. This is the test for determining whether the correlation coefficient is significantly different from 0. And since R squared is simply R squared, it's the test for the correlation coefficient as well. In this illustration, it's testing whether the amount of time parents read to their child accounts for a significant amount of the variance in child reading ability. Now, the regression degrees of freedom is equal to k, which is, in regression, equal to the number of predictor variables in our model. The residual degrees of freedom is equal to n minus k minus 1. This equation applies to both simple regression when we have a single predictor variable, as well as multiple regression where we have 2 or more predictor variables in our regression equation. But based on characteristics of the sums of squares and degrees of freedom that we just discussed, in simple regression, this equation can be simplified a bit. First, we saw that the sums of squares regression and the sums of squares residual are proportional to r squared and 1 minus r squared, respectively. We can substitute them into the equation. Also, in simple regression, k, the number of predictor variables, is just 1, so the regression degrees of freedom is just 1. In that case, our numerator reduces to just r squared. Similarly, the residual degrees of freedom is n minus 1 minus 1, or n minus 2. So this is the same formula, just expressed in terms of r squareds instead of variances, and with the degrees of freedom incorporating the fact that we only have a single predictor. So this F-test examines whether the overall regression model is statistically significant, focusing on the variance that's accounted for by our regression equation. It's testing whether the variance is statistically significant. Now, there are other ways to look at effects within regression, and that's particularly true in multiple regression. But we can also examine them in a more simple way here, and we'll get into that in our next video when we look at testing the regression coefficient. But that's it for now, okay? Take care.